Hello world, Joshua here. I'm going over the problem of LeetCode, binary tree in order traversal. I'll include a link below in the description, and you can feel free to try to solve it on your own before I try to go over it myself. So the problem is given a binary tree, return the in order traversal of its nodes values. So here's an example of a tree. This is what it will look like. And then when you output a list, you should have it in order traversal at 1, 3, 2. Now, you might have some questions. One, what's a binary tree? True. What is an order traversal? And three, okay, a tree. At least tell me what's a tree. So a tree can come in many shapes and sizes. Sometimes in the office you can see a ficus tree. Oh, not that tree. I'm sorry. I think you meant. I'm just messing around, guys. Now, here, let me just start with this one. A tree it's like a type of data structure. Basically, the concept of a tree is that there's a node, and that node has nodes below that. The node that has nodes below that is kind of referenced as the parent, and this parent has several children below that. Now, if there's a node, a parent that's just like the only one at the very top, as you can see right here, that's called the root value. And then for each level below that, that's as I mentioned. There's a level below that. That's level 1. It's level 2, level 3. That's like almost like father, mother, grandfather, grandparent. It's almost like in that sort of fashion. Like you have different levels of hierarchies of family order. Actually, let's not get carried away with that one. So at least you know what a tree is. It basically has a parent with children values below that one, and that children could have children below that. Now, what is a binary tree? So in this case, as you can see, like in this example, this example is not that really good, but a binary tree is that, as I mentioned, there's a parent and there's some children. In a binary tree, every parent has up to 2 children. So here, this part right here, that's this part right here, this whole part right here is be a binary tree. Now this part won't be. Okay, by the way, when I say binary tree, this whole structure should be a binary tree. But since I don't have a good example right now, and I don't want to search it up and save some time, see this as 2 children. Technically, if this were its own sort of tree, that would be a binary tree because it only has 2 children in that node. Or if it has 1 children, that counts too. But if it has 3, that's not a binary tree anymore. Now, you might be asking, okay, I think I have an idea what a binary tree is. How do you in order traversal that? Actually, what does even traversal mean? Traversal means to travel. So you can see right here, you can travel through each of these values. I mean, you can see that there's direction to it. In this case, there are 3 ways to travel. Actually, let me just go step a bit back. Okay, so there's 2 ways to travel. One, you can go travel here. Take this example. You can go all the way down and explore to all the values. Go through all the way to the tips of a branch, and then you just go explore. Let me see if we could find a formal definition. Actually, hold for a second. Yeah. So a best way to explain a depth versus traversal is that you traverse through the depthward motion. You go all the way through the very tips of the branches. And then keep going on, and then if you see a dead end, like if I go all the way down here, I go back up here, I check this one, go back up and go check to the rest of the tip of the branches here, and so on and so forth. You don't even have to start this way. You can start this other direction as well. The second way is called breadth first traversal, and you can look at that on your own. That's when you explore each of these nodes by level. So this is the first level I check, this is the second level I check, this is the third level I check, and so on and so forth. In here, I say the best way to solve this is a depth first traversal, and actually that is the only way to do that. I think my tree knowledge is a bit rusty, so here, because what I understand is that depth first traversal, there's 3 different ways to traverse. There's in-order traversal, and there's pre-order traversal, and there's post-order traversal. Now what does that mean? So let's just focus on one right now. I'll just tell you one of them, which is what we need. In-order traversal. That's when you traverse through the left part of the subtree until you reach an endpoint. After that, you visit the root of that tree, and then you do some sort of action to it. You could display that value. In this case, that what we're doing right now, we want to add it to a list of that in order value. And after we're done, we visit the right subtree until we reach a dead end, and then we repeat this whole process over and over again. So you can see right here, okay, left subtree, there's none. That's a dead point. So we add it to the list, and you can see here, there's a 1. Now explore the right subtree. Okay, it has a left value at the subtree, so we go there. That one doesn't have any subtrees in its left node, so we just put 3 as a root value into the list. It doesn't have any right subtrees, so we just go back up right here to number 2. Now that one, we put that into our list, and then there's no right subtree, so we just add it in, and there you go. 1, 3, 2. If you have any more questions, just feel free to just look up binary in-order tree traversal. Anyways, now let's just actually take an example here. So we want to traverse these, traverse through this tree, and as we traverse, we add these values to a list. So let's think about this for a second. All right, so my first instinct, what I'm more familiar with based on my experience, is that you can create a list, and then, as you can see right here, these are integers in what we're going to be traveling through. We want to output a list of integers, basically the values of each of these nodes. So say list nodes. Oh, sorry. I'll make this global because I'm going to be doing what you call a recursive call through this tree. I'll explain more about what is traversal, what is recursion. Hold for a second. So I'm going to go first. I'm going to initialize an array list of integers. That's where we're going to store our values. Next, I'm going to create a recursive call to explore this whole tree. And as I explore that tree, when I'm done, I'm going to return that whole list that has been created from this recursive call that I'll be creating right here. So I'm going to create this helper function right here. You just have to. I just add this return call because it might help us eventually. I'm just gonna keep that in mind. Traverse tree node. This is the input. We put input, which is the tree node root itself. But I'll explain more about recursive calls for a second. So what is a recursive call? A recursive call means that it's going to keep performing an action until a base condition is met. In this case, let me explain it more better. It's better if I do it per this example. If I explore and I found out, like, okay, so I'm going to go to the left subtree here, right? You can see each node has these properties right here. There's a left and right. It points to either the left, right, or a val. Now, if it has, the base case that I want to check right here is that if it travels to, let's just say starts at 1, goes to the left subtree, and if that node equals null, in other words, that actually is a better way to put it, that node never even existed at the left subtree, then we return null. We go back up. So we're back here, back at 1. Now, what do? Now we continue. Actually, okay, so if it's not null, which is say we're back up here, let's just follow the order. A best way to give you an example is like this Inorder Traversal right here. See, you just traverse left, then you call the recursive call again, and you visit the root and traverse the right subtree, and so on and so forth. So okay, I'm going to make the call right now. Traverse node. Sorry, node.left. I want to explore if there's anything else in the left subtree. If not, I go back up to the root value, and now, as I mentioned before, I'll add it to the list. This is what we're going to do in our in-order traversal. We're going to do something with that root value. We'll add that node value into that. And now we're going to traverse to the right to see if there's any subtrees. So you can see right here, I explore the left subtree. Then if there's nothing there, I just go back up until I reach that root value, and I'll add it to our list. And then I explore to the right subtree. Then I return node. Okay, yes. So I include this tree node, this return type as tree node, because it will help us determine if that base condition is met, whether it's going to be node is equal to null, or if it's going to be something, we just continue along with what we're doing right here. And I made this global so it'll be easier for me to just add the nodes right here, and I could just return nodes right away without any issues. And let's see if that works. Hooray! Now if I submit this one, hold for a second, guys. Yeah, I've been practicing this problem for a bit. Awesome. I think I solved that problem. Oh. Da-da-da-da. Could you do it? Oh, no. Okay, so now I can't do a recursive solution for this. I have to do it iteratively. So in the recursive solution, you can see right here, the structure of that is that basically the function calls itself over and over again until it meets that base case or base condition. It doesn't want me to do this because according to this problem, they see that as a trivial answer. It wants us to solve this. It wants us to solve this with through iterating through it, like iterating either with a for loop, while loop, something loop. So let me think here. What can I do? Well, a base concept of, I don't know if you're familiar with this, but there's something called a stack. I don't know if there's a hint here that tells you that. Okay, so there's something called a stack. So what a stack does, let me see if I could just type that up. Actually, let me just do this right here. So stack is that you put values inside this data structure. 1, 2, 3, 4, 5. And if you want to make it return a value, you have to pop off the last value that was entered. So we'll just say in this case, if you pop it up right now, if you pop a value, it's going to be 5 because that was the last one entered inside of it. The principle that this data structure follows is that last in, last out. Oh no, last in, first out. Basically, you know, the last thing you put inside this data structure will be the first one to exit out of it. Now, why did I mention that as something that could help us right now? Well, if you think about it, if I think about this, from my experience, I know I practiced this a bit before, but if you try to conceptualize it right here, if we're going through this tree, we know that we started with 1, but we don't want to do anything with that yet. So we put that technically in our stack, like we'll deal with that later. Since there's nothing left subtree, we need to go and pop that value up of 1, and we'll do something with that. And then in this case, we'll just add it to our list, and we go to 2. Now we add 2 to our stack, and okay, we have something in 3, so we add 3 in our substack. So here, I'll just give you an example. 2, we put 2 in the stack. It has something in its third value, so we actually go and add another thing to its stack, which is 3. Now, since that it has no left subtree, we have to pop it back up, and we have to do something to this 3. In this case, just add it to the list. That's how I could see the stack could be applicable right here. It's following that sort of order. The Inorder Traversal has that concept of how we can use the stack into this problem. So let me try to actually solve this one here, so that maybe it might be helpful if you see a good example. So let's see here. So in this case, I suppose that it'll be done iteratively, so I could just put inside my public function. And as a matter of fact, I could just initialize it right here. It would be an array list. Integers. Oh shoot. All right. Now what? So if I have it here, I want to also initialize a stack. This stack will hold a bunch of these tree nodes. Okay. Now what's next? So as it iterates through each of these nodes, I need to be able to point to, okay, we don't want to lose track of what nodes have been. So as we traverse these trees, we need like some sort of like address, a locator, like pointing to that part of the tree, so that we can just perform our functions into it. Like we want to get this value. Do we want to go and see if there's a left subtree or right subtree at that area? We need like a pointer. In this case, and while we have a pointer, we had to keep it separate from the actual binary tree itself. So this is what I create right here. I think I'll create a tree node pointer, so that I could just I'll be like, hey, I want to see what's happening here. Hey, I want to see what's happening here. It's literally pointing to what are we, where are we doing our processing of the data in this location. Here, it's going to be pointing at the root because that's where we're going to start. And when we start right there, we'll do while pointer is not equal to null. If it's equal to null, or first, if the stack is empty. So there's two things I want to consider. I'm going to stop doing, like, I'm going to stop check. If the pointer is pointing to, like, let's just say, like right here, that means it's not null. And I can, hold for a second, let me think about this. Okay, so the pointer is not null, so definitely I have some exploring to do. So I have to perform a series of actions on the tree. I should actually look up a binary tree to be a better example. Sorry about that, guys. Maybe when I'm refactoring my videos in the future and I'm a better teacher, I can provide better explanations. I'll definitely do that. Just leave comments in the below and I'll provide a better explanation. Now, okay, while I'm checking right here, I also want to check. Okay, so specifically now, we know that the pointer, let's just take the scenario that the pointer is not equal to null. What should we do? If it's not null, we want to push that value, the node right here, into a stack, because we want to deal with that later. We want to deal with that node later. We just want to first check if there's anything in the left subtree. So right now we're just going to put this in our schedule, per se. You know, like we'll say, we'll deal with this later when we need to. And we keep exploring that left subtree. There you go. Alright, now what? Now, well, let's say we reached a point now at the pointer. Let's just take this part right here. I put 1, okay, I see something, it's not null. I'll put it in the stack. I'm pointed out left. Uh-oh, it's null. So what should we do now? In that case, we want to revisit that last node that was not null. So we pop that value back up. Alright, A1, what can we do with you? 1, we want to first, as per the rules of Inorder Traversals, oops, I'll put nodes.add the pointer.value. I want to add the value there. And now I want to see if there's anything to the right side of that node. And if all is well, oh, and if I go back here again, so let's just say I add the 1, I check its right subtree. Okay, now we have something there. We push that value inside. Now we have something again, and pointer.left, we push it back in there. And now we're back here again. The pointer is now equal to null, so we pop back to 3. We add it to our list, and then we go back up to 2. We pop it, add it back to our list, and now we have that full Inorder Traversal list. So let's see if that works. Oh, and I forgot, you have to always return that list at the end. So let's hope that works. I'm going to run the code. Huzzah! Hooray for science! Let's submit it to make sure if it actually works. And ta-da! We have both. I've shown you both. 1, recursive solution. Excuse me. And 2, the iterative solution to solving this problem. Thank you for watching, guys. If you have any questions, please leave it in the comments below. If you have any criticisms or any ways that you suggest that I could be better at presenting my video, definitely add it in the comments. I want to be a better teacher. I will be a better teacher, but only if you help me likewise. And if you like and subscribe or leave comments, I'm going to give you a brand new TV from the 1920s. So if you want to watch the Dick Cheney show, oh, is it called the Dick Cheney show? What is it called? Dang, I don't know if there's any TV shows back in the 1920s. Scratch that. I'll give you TV shows from the 1950s. We're gonna watch the Three Stooges. If you want some humor in your life, you want to see Moe and the other Stooges, then like and subscribe in this video, and before you know it, when you open up your eyes, you'll be staring into the ceiling where the TV is going to be flashing the Three Stooges. Just kidding, guys. That was a pretty bad joke. So I'm going to exit out of this video as fast as I can before there are any repercussions